Okay, so let's start for today. So last time I finished talking about the power series, right? So and then at the end I told you that if we have a function, okay, which is called the analytic function, okay, so then that means that this function can be expressed in terms of a power series like this, okay. And of course, okay, so this power series is a convergent power series, right? Because for this function here, right? So for a value for input value x, okay, so this function also give me just some value, some number, right? Some finite value. So that means that I require this series has to converge. Okay. So today I'll talk about how to actually find this power series. So given a function to you, right? So an analytic function to you. Okay, so how do I find a power series? Okay, so that represent this function, right? For example, I give you sine of x or cosine of x, right? So how do I find this power series? And last time, right? So I told you that for such a power series, okay, so it will be a uniquely defined power series, okay, for a function, okay. So then if I write in this form, so that means the question is, how do I find a of n, right? So that's the question. How do I find a of n? So and today, so what I'm going to talk about is the so-called the Taylor series. Okay, so probably for some of you, you might have already learned it already. So here is the idea. Okay, so I have, well, as I said, this function can be written as a power series like this, right? So this function is an infinitely differentiable function, right? So it is an analytic function, and then well, at least, okay, so this function is infinitely differentiable in some region, okay, near this value x equals a. Okay, so and then this is the power series that I have over here. So how do I find a of n? Okay, so first of all, if I simply put x equals a, okay, so this power series itself, of course, has to give me back the value of the function at x equals a, right? So that is, right, so if I just simply put x equals a, then the left-hand side will be f of a. Right? And then the right-hand side, right, so I just put x equals a, right? So then I have this a naught plus this infinite sum, but this infinite sum is simply 0 because I have this a minus a over here. Right? So that tells you that this a naught has to be equals to f of a. Okay. So we figure out the first term a naught. Okay, so what about the next, and then also the one after next, and so on. Okay. So the trick is to actually take derivatives of this function f of x, right? So if we are going to take the first order derivative for the function, okay, so then the series, okay, so becomes a1 plus, okay, so the sum of the terms over here. Right? So on the right hand side, so all I do is that I do differentiation for this series term by term. Right? So we know that we can do it because it is a convergent series. So that's why I'm allowed to do the derivative term by term. Right? So if I go to do a term by term derivative over here, then you can see that basically, so every time whenever I have this x minus a to the n, then it just becomes n times x minus a to the n minus 1, right? So this is what I have here. Okay, and in particular, okay, for a naught, okay, it will just be gone, right? So because for a naught, the first term is just a naught, but without any x term, right? So then that one is just a constant. So that means after taking derivative, the a naught disappear, right? So then the first surviving term is simply just a1 over here. Okay. So then now if I just look at it, right? So again, I require that when I put x equals a, right? So then the left-hand side, of course, it's just f prime a, right? And then the right-hand side would be a1 plus this sum, right? But then again, I have this a minus a over here, so this sum is 0, right? So then the right-hand side would be just a1. So therefore, we find that this a1 is just equals to f prime a. So then we do it again. Okay, so take the higher order derivative, second order derivative. Then what you will be able to find is that a2 will be equals to this f double prime a divided by 2 times 1. Okay. So using the same ideas, right? So you go to keep doing derivatives, right? So find the kth order derivative of this function. Okay, so and then eventually you'll be able to find that for any integer k, this coefficient ak is equals to the kth derivative of this function. Okay, so put this x equals a divided by k factorial. Okay. So this x has to be set to a. So therefore, the Taylor series, okay, so for f of x about this point, x equals a, if I just write out all the terms, it looks like this. So here, okay, so this is mathematically, we know we just show how to find out all the coefficients individually. Okay, so but let's look at it geometrically to see whether it makes sense or not, right? So because eventually, right, so we have so many terms add together. Okay, so and we expect that all the terms sum together will be equals to the function, right? So, but of course, practically we don't take all the terms, right? You just practically cannot do that, right? So and then so that's why let's look at, okay, so the first couple terms, okay, so to see whether how similar, okay, the shape of this curve composed of the first couple terms on the right hand side to the left hand side of the original function. Okay. So here let me just draw a picture. So suppose I have a function, right? I have a function like this, suppose, and then so this is, and then the Taylor expansion, right? So if, as I have from the last slide, so let me just consider the first term that has an x in it. Okay, so this is okay, we know that we need to add many more terms, but if I just look at these terms over here, what does it represent, right? So that means on one hand, so okay, so I have this y equals f of x, and then on the other hand, I'm going to draw y equals f of a plus x minus a f prime a. How does this curve look like? So if you go to just rearrange the term, so first of all, you can clearly see that this is a straight line, right? Because you have this linear term in x. So this one can be written as y minus f of a divided by x minus a equals f prime a. Okay. So this is clearly an equation of straight line. So what it tells you is that this is a straight line that passed through a point so suppose this is a, right? So then this would be f of a. So then this point is a f of a, right? So the x coordinate is a, y coordinate is f of a. So, and this line passes through this point, right? So from this equation, you can see it. So now, what is the slope of this point? Okay, so the slope of this line. The slope of this line is given by f prime a. And what is f prime a? So actually is the slope of the tangent of my original function, right? So this is the slope of this line. This purple line is exactly f prime a, right? So therefore, okay, so this represents the line that is tangential to the function at x equals a. Okay. So then now you can ask, okay, so how similar is my or how close is my line here to the original function? Okay. So if you look at it, you can see that of course exactly at this point. Okay, so the two lines touch each other, right? So but as you go further and further away, okay, so then the vertical distance between this blue and the green line can be getting larger and larger, right? So you can see that if you are, as long as you are rather close to this green dot here, then the distance between the two lines are rather small. So then that means, right, so this is a rather, well, not a too bad approximations. Okay, so for this function f of x, as long as you are not too far away from your point A. Okay. So in fact, there's another way to interpret this terms over here. Okay, so let me draw another picture and define the function in a different way. Okay, so suppose okay, so I'm just drawing over here. Let me just draw it over here. So this time what I have again is just a curve like this. And then this time, okay, so this curve over here is not y equals fx. Instead, this is y equals f prime x, suppose like this. Okay. And now I will just define another function. Okay, so which is the area under this curve. Okay, so this area over here. So what is the area under this curve? Right, so you know that this is the area over here is actually the integral of this curve, which is f prime x. So in this case, I start from 0, right? So, but it doesn't matter. So, and that's why this a function, this area function, is actually equals to simply f of x. Okay, so and actually you're off by a constant over here. But let's say f at 0 is 0. Okay, let's say that. So then this area function, okay, so then in this case is actually just f of x, right? So this is f of x over here. Okay. So then this is x, So now, if I am going to consider again this one over here, okay. So what it really means. So suppose A is over here, okay. So then this green area, this green area alone is f of A. Okay. And on the other hand, right? So your f of x is the entire blue region, right? So which is approximately equals to this green region over here plus this rectangle, the area of this rectangle over here. Okay, we are off by a little bit of residual area over here. Okay, but you can see that, right? So f of x, or let me just yeah, f of x is approximately equals to f of A plus this rectangular bar area. Okay. So what is the rectangular bar area over here? So you can see that, so it's just the base width times the height, right? The base width is x minus A, right? So the base width is just this one over here, so which is x minus A, okay, times the height. So the height, I'm just taking this point as the height. So then this height is f prime A. Right. So all I'm saying here is that the blue region area is equals to the green region area plus the red region area, approximately. So then you can see that this is just another way to see the first two, the meaning, the geometric meaning of the first two terms in your Taylor series. Okay. So in fact, okay, using this series, okay, so we can also interpret geometrically how the second term, or the second order terms in X works, right? So basically, what we are going to do is to try to also consider this small area over here, right? So because here you know that our approximation is not perfect because we are off by this small little triangular-like area up here, right? So let me try to draw a bigger version of that triangle. So I'm just going to, right, so zoom in this part. So what I have here is a triangular-like region that looks like this, right? So what is the area of this region, right? So if I actually just, this is still, right? So it's not exactly a triangle, right? So, but then if I approximate it as a triangle, so what I'm going to do is to take this tangent line, okay, over here, and then I'm going to find out this area. Okay. So what is this shaded region area? So that means I need to find the base width, right? So the base width again is just x minus A, right? So what about this height over here? So to do this height over here, okay, so I need to actually find out this angle. Okay, this angle I call that theta. And the the height over here is actually x minus a times tangent theta, right? And this tangent theta, right? So that means is the slope of this green line, and the slope of this green line, so is exactly the derivative of this curve over here. Right? So the derivative of this curve at this point, okay, which is taking the derivative of f prime x. So that's why the slope is actually f double prime. Right? Then I take the slope at x equals a. Right, so the slope is this f double prime a, and which is my tangent theta. So therefore, the area of the triangle is x minus a times x minus a times f double prime a, and then times 1/2 because it's a triangle, right? So therefore, right, so the next term is 1/2 x minus a square f double prime a. So geometrically, okay, so we can see the y, okay, so this term, okay, give us a further improvement on approximating the function over here. Okay, so I think practically, at least in the physics course that you take later, okay, so most of the time, okay, so it is sufficient for you to just use this first term, which has a linear term in x, and this second order term, which is a quadratic term in x. So most of the time, that is sufficient for you. Okay, so then let's do a simple example. Okay, so then I'm going to let's do a simple example over here. Is that if I have y equals f of x, which is equals to e to the x, an exponential function. And then I want to find the Taylor series. Okay, so at x equals 0. So what do I need to do? Right? So and then I just show you the general formula, right? So the f of x is equal to f a plus f prime a x minus a and so on, right? So and here I will set a equals 0, right? So then what is f of 0, right? So f of 0 is just e to the 0, which is 1, right? And then what about the derivatives, right? So one nice thing about exponential function is that no matter how many derivative you take, right? So the result, it just becomes the function itself, right? So that is, right? So the f of n x, so the nth order derivative of x is just given by e of x, right? So for n equals to 0, 1, 2, any n. Okay. So therefore, at 0, any order derivative will just give you 1. So that means this is 1, this is 1, this is 1, and so on. So therefore, the exponential function e of x is given by 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on. So here is a graph. Here, instead of this graph is doing e to the t instead of e to the x, but you know. So the solid line over here, okay, the solid black line over here is the original function. Okay. And then the first term, right, so 1, which is just f of 0, is just this horizontal line over here. Right? So this is a 0th order. So then including the second term, okay, which is the 1 plus t. Okay, so then I got this red straight line over here. Then you can see that, of course, this red straight line would be a better approximation than this orange line over here, because you can see that as if you are somewhere not too far away from 0, right? So the distance between this red line and this solid black line is not too far away. And if you include one more terms, right? So then you get this green curve over here. You can see that it's a further looking more similar. Okay, so closer to this black line over here. Right, so, and you can just keep adding terms, right? So this red dashed line over here. I'm sorry, this black dashed line over here, and then this blue dashed line over here. Right, you can see that more and more terms are approaching the original function better and better. Okay, so here are some Taylor series for some elementary functions that you use a lot, right? So the e to the x is the one that we just did, right? And then you can see that this sine of x and this cosine of x are given here, right? So one interesting thing you can see is that for sine of x, you don't have all this even term in x, right? So, and then for cosine of x, you don't have all this odd term in x, right? So that means that when you take the odd order derivative and then set x equals 0, right? So the value is 0, right? And it actually makes sense, right? Because you know that this sine of x is an odd function, and then this cosine of x is an even function. Okay. So for all these three cases, okay, so this Taylor series would work for all x. Okay, so meaning that no matter what x you put in, so this is a convergent series. Okay. But one thing to notice is that well, given that you include just a finite number of terms, right? So practically, right? So and the closer you are at 0, the better approximation it gives, right? So as I already show you this graph over here, right? So adding more and more terms, okay, so the overall, right, so getting better and better, but still, right, so you can see that if you're far away from 0, right, so the distance between this blue or this dashed black curve to the original function is can be quite far away. So therefore, okay, so sometimes if you just want to approximate, right? So the function using Taylor series, for example, at this point, rather than at 0, then you should do the Taylor expansion at this point, right? So because in the closer it is at with the expansion point, okay, so the better approximation that you get, right? So in this case, because the expansion we did is at x equals 0, so that's why the approximation is the best in the region around x equals 0. Okay, so then in the fourth case, okay, log 1 plus x is also a function that that you use quite often. And here, so you need to be careful about the interval of convergence over here. Again, this one I already talked about in the last time. Okay, so how do you test the interval of convergence? So, and you can try to, right? So as an exercise, try to verify the intervals of convergence for all these series above. So another example over here is that I want to find the Taylor series of this function. Well, you can see that there's no any tricky parts here, right? So you just need to keep taking derivative of this function, right? So, but one thing that actually could make our life easier is to recognize the fact that this log of 1 plus x divided by 1 minus x is actually equals to log of 1 plus x, okay, minus log of 1 minus x, okay. And then because log of 1 plus x is a series that we already found here, right? So, and then, well, with this, you can also immediately find out log of 1 minus x, right? So you just need to replace this x by minus x. And then what you need to do is just to put your series for log of 1 plus x here, and then put your series for log of 1 minus x here. And then you do this term by term subtraction. Okay. Again, right? So you are allowed to do that. So if you know that, right, both series converge, okay, so at the value that you are trying to do subtraction, right? So in the last slide, so here I already told you that the interval of convergence for this log of 1 plus x is that x has to be lie between 1 and minus 1, right? So in fact, right, you can show that for log equals for log of 1 minus x, right? So the interval of convergence is also this one, right? So that means that the common interval of convergence is, right? So just this. So that means as long as you consider any value of x within this region, right? So you can do the term by term subtraction. Okay, so for these two series, and then get your result. Okay. Right. So then this is just the answer over here. Right. So as I told you, right? So practically, so although we can find out a general formulas, okay, so for any terms in the Taylor series, but you are not going to take infinitely many terms in your actual calculations, right? So then you are only going to take the first few number of terms. That's it. So, and if you just, that means you are going to do a so-called truncation, right? So that means you are just going to take the first few terms, and then you just ignore the higher order terms, right? So then what you have now is nth order polynomials. So instead of an infinite series. So then if you take the first, here actually I should say n plus 1, okay, because the first term, which is just a constant term, is known as the 0th order. Okay, so then that means I should actually count this term as the first term. Okay. So anyway, right, so as I stay here, right, so at the nth order polynomial, okay, for function x is the first n plus 1 term, okay, of the Taylor series of f of x. Right. So then you can see that, right, so the first order polynomial, right, so the second order polynomial, nth order polynomial, right? So the nth order polynomial, right, so the, is that the highest order of x exists in this whole thing is x to the n. Okay. So this is just another graph for you, right? So just now I show you the graph for the exponential function, how the including more and more terms give you a better and better approximation to the function, right? So here, just another graph for this sine of x. Okay, so you can see that which one is the sine curve, right? This is the sine curve, of course, is this blue one over here, right? And if you're going to do the Taylor expansion at x equals 0, actually, I gave you the answer already, which is this one, right? So then what you're going to do is that if you include the third order only, include up to the third order terms only, then you get this curve over here, right? So, and you can see that it's doing very well in this region, but as you go further and further away, then this is getting way off, right? So now n equals 3 and then n equals 5, right? So you cannot do n equals 4 because you know that the n equals 4, I don't have a fourth x to the fourth term for the Taylor polynomial of sine of x, so that's meaningless to say about n equals 4, right? So n equals 3, then you need to jump to n equals 5, then you get this curve over here, okay, and then n equals 9, n equals 11, right? So you can see that how this including more and more terms will becomes closer and closer to the original function over actually over a wider and wider range. So then one more question is that now we know that practically we cannot include infinitely many terms. We are only to include a number of terms. But how do we know whether we are doing a good approximation to the original function or not? So that is how much we are off, right? So, and this Taylor theorem, okay, so can actually help us to estimate that. Okay. So the Taylor theorem tells us that, right? So this function over here, right? So can be expressed as an nth order Taylor polynomial plus something, some function. Okay, first of all, this is not surprising, right? Because we know that from Taylor series, right? So we know that it is an infinitely long series, and then you have the nth, the first n plus 1 term plus infinitely many terms, right? So, and then here, well, when we write it this way, so that means that the remaining infinitely many terms is hidden, is contained by this function, which I call this R of x, right? So that's nothing surprising here. It's just that I call this remaining sum of the terms R of x. Right? So, but then of course the question is how significant this R of x is, right? So, and this Taylor theorem actually tells us that this R of x can be just written as a single term like this. So this one, what does it look like? So it looks like there's this the basically is the next term after this term, right? Because this is x to the n, this is x to the n plus 1. But one important difference over here is that you can see that this derivative over here is not taken at this alpha. Okay, instead it's taken at some unknown number cx, which is lying between alpha and x. Okay, so that is right. So if again, let me draw a picture over here, right? So I have a function again. And then I have my nth order polynomial. Let's say it's something like this. You know. So let me just call this Tn of x, right, to tell you that this is an nth order polynomial. Okay. And then this is my expansion point. Let's say this is my expansion point alpha. So, and now if you are somewhere, if you consider some other value, right? So on the x-axis, if I consider some value over here, x, right? So, and then the difference, right? So between this nth order Taylor polynomial and the actual function is given by, again, right? So this vertical distance over here, right? And this vertical distance is represented by this R of x, right? So this R of x, right? So it's something that we want to know how big it is, right? So, and the Taylor theorem tells us that it can be written like this, right? So, but, right? So it's not going to tell you exactly how much you have over here, right? So because, as I said, right? So Cx is some number that we don't know what it is, right? The theorem only tells you that it exists, and it is somewhere between this interval. Okay, Cx can be somewhere here. Okay, so then, although, right, so these Taylor theorems cannot tell us exactly how much we are off, right? So from the real value, but it can help us to do an estimate. Okay, so on the difference that we have, right? Right. So here, right. So I have the difference. Okay, so between the nth order polynomial and the actual function. Okay, defined like this. Right. So this our epsilon x. Okay, so this epsilon x essentially, right? So actually it's just the R of x over here. Okay, so that's nothing. This epsilon x, I'm just using a different notation, but this, you can see that from last slide, this epsilon x is actually equals to minus R of x. Okay, you can just do the subtraction here. You're able to see that. So now, right? So from the Taylor theorem, right? So we know that this epsilon x is given by this, and then now if we're going to take the epsilon sign, right? So for this epsilon of x, then I got this. I have to do the epsilon sign for this whole term, right? So now the term that we don't exactly know is this one, right? So as I said, because Cx, the Cx value is something that we don't know. Okay. However, you can find out, right? So the upper bound, right? So for this term over here, right? As long as you can take the derivative, then you can always find upper bound for this term over here, right? So for example, if I give you cosine of x as my function, right? So you can take derivative n+1 time, right? So you can, well, you know what it is. You will either be a sine or cosine, and then from there, right? So you can know what is the maximum value, okay, of that function. Okay. So then that's why, right? So if I am able to find out the maximum or the upper bound of this function, okay, so then I can write this error function, okay, so to be smaller than or equals to this whole term over here. So therefore, right? So this term is the upper bound of the error, okay, for the nth order Taylor polynomial. Okay. So here is an example. Okay, so suppose, right? So I have this function 1 plus x to the power 5. Okay, and then I use the Taylor polynomial. Okay, so to approximate this function. Of course, you first of all you actually understand that this for this function itself, in principle, you don't need to use the technique of this Taylor polynomial or Taylor series, because you can just expand it, you know that the last term you have is x to the fifth, and that's it, right? So but here let's test the idea, right? So instead I'm going to just find the Taylor polynomial. Okay, so for this function and up to the third order already, right? So that means that the Taylor polynomial I have would be something plus something x plus something times x squared plus something times x cubed, right? So this is a Taylor polynomial that you have, and of course you know that this one won't be equals to this one. This one has the x to the 5, right? This one only up to x to the third. Okay. So but then how do I estimate the error, right? So using what I told you in the last slide, right? So I just consider this term over here, right? So the fourth order derivative for this 1 plus x to the fifth, right? So you can go ahead and do that, and then you find that this whole term, it just becomes this one over here. So and because, right, so I'm going to just consider the x, okay, so within this range as stated in the question, and then that means, right, so this cx, right, so although I don't know exactly what it is, but I know that it has to be within this same range, right? So and therefore, right, so this 1 plus cx lies within this range, and the maximum, therefore the maximum absolute value of the absolute value of this 1 plus c is just 1.5. So therefore, right, so this one, right, so the absolute value of this one at most is 1.5. Okay. And therefore, the error that I would have is smaller than or equals to this 5 times x to the power 4 times 1.5, which is this 7.5 x to the power 4. Okay, so here let's take a 10 minutes break. Okay, so we'll come back at 12:28. Okay, so and then after that I will tell you the Taylor polynomials for functions of 2 variables. Okay. Okay, so let's continue. So this time, as I just mentioned, so I'm going to give you the Taylor polynomials for a function of 2 variables. Okay, so we remember that if we have a function of 2 variables, so what we have essentially is a curved surface in the xyz space, right? So and then therefore, right, so the Taylor polynomials that we'll have, of course, will also be a function of the 2 variables. Okay, so or I should say that it will be a polynomials that depends on the both x and y, and then if we draw the polynomials, it will also be a curved surface in this xyz space. Okay, so here I just give you the form, okay, for the first order, okay, and the second order Taylor polynomials. Okay, so I just show you the form first, and then I will explain a bit why they should look like this. Okay. So what you have here, the first order is that I have a constant term over here. Okay, so what I'm doing here is that I have this function of 2 variables, right? So and then I consider a point, a particular point A, B, right? So and then I expand the Taylor polynomial at that point. Right? So here, right? So the constant term over here is f of AB, right? Exactly at f of AB, right? So and then I have this term over here, right? So which is given by a linear term x minus a, right? So and then times the partial derivative with respect to x at this point AB, and then the other term over here is that this linear term in y times the partial derivative of y at a and b. So first of all, why does it make sense, right? So if you go ahead and put the x equals a and then y equals b, right? So what you have over here is that you have this a minus a. So this term goes away, and then this y minus b, which is b minus b, then this term goes away, right? So that means, right? So at least this polynomial will give me a correct value of f of xy at this ab. And right, so and also, right, so if you try to take the derivative, right, so on both sides, right, so what you see is that if I go to take the derivative for both sides, so then the left hand side, well, let me say take the partial derivative for both sides, right? So the left hand side will be this, and then the right hand side will be what? So this is just a constant, and it goes to 0. And then if I take the partial derivative with respect to x for this point, and then basically I'm just taking partial derivative on this, right? So then this is just 1. And then if I take the partial derivative with respect to x for this term, this whole thing is 0 because there's no x dependence over here, right? So that means the right hand side, right, so will also give me back this one, right? So at a b. So that means, right, so if these polynomials, right, so will also give me the correct value of partial f partial x at ab, right? So similarly, right, so this polynomial will also give me the correct value, right? So of this partial f partial y at ab. Okay. So and if you go to the next order term, right? So basically, the strategy is again is require that for this time, right? So I require this polynomial to give me correct values of the following. So that is, right, so if I write it in this form, right, so you realize that this polynomial, okay, so at x equals a, y equals b, it will give back the correct value, right? So for this three second order partial derivative, right? You can go ahead and try by yourself, right? So that is, right, so the idea is that you are basically going to assume that this function f, x, and y, okay, so can be written as a form like this. Right, so you're assuming that this function of two variables written as this power series again, right? So but depends on both this x and y, right? So and in principle, right? So these two sums are summed to infinity, right? So and if you go ahead, right? So as I said, if you keep taking derivatives, right? So on both sides, and require that they have to be equal to each other, right? So at x equals a, y equals b, you are going to be able to figure out a mn. And in fact, I didn't write it here, but if you want to know the general formula, right? So you can actually find that if the general formula actually looks something like this. Okay, so if you want the nth order, the capital nth order Taylor polynomial, okay, so this is what you need to do right here, and this index over here, right? So it tells you the order of derivatives that you need to take. Okay, but again, okay, so you are practically, right? So I believe most of the time, okay, so the first or the second order Taylor polynomials will be sufficient for you. Okay. So again, let's look at the geometric interpretation, okay, so of this Taylor polynomial over here. Okay, so why this one is close to our actual function f of xy. So again, let me draw a picture over here. So this is my curved surface. Suppose the function looks like this, right? So this is my I call this z equals fxy. Okay, and now I'm going to consider a particular point, right? Let's say this point in the x and y coordinate is this AB. Okay, I want to do the Taylor expansion, right? So about this point. So remember, in the first in the one variable function case, right? So if I have a function and the first order Taylor polynomial is a tangent line, right? So you still remember that, right? So xy, this is the function, and then the first the first order Taylor polynomial is this tangent line. So then naturally, in this case, we have a curved surface, but you expect that the first order Taylor polynomial will be a tangent plane, right? A flat plane that is tangential to this curved surface at this point, right? So, to try to draw it, there will be a plane that perhaps looks like this, right? Okay, so maybe it's not a very good drawing, but you just imagine that this purple plane, okay, is touching this green curved surface at this red point, and also is tangential to right, it's tangential to this green surface. So then, okay, what is the how do I represent this plane, right? So as a function, right? So for those who know how to find the equation for a tangent plane, you know, I think you know it well already, but let me just say it. So if I'm going to find the equation for this tangent plane, okay, so what I need to do is, first of all, I want to find a normal vector. Okay, so I want to find a normal vector for the plane. Okay, so normal vector, again, I'm just going to use this n to represent it. All right, so the how do I find this normal vector n, right? So this is a normal vector for this purple plane, and at the same time, it's also the normal vector for this green curved surface at this point, right? Because the two are tangential. So then remember what we learned in chapter 3, right? So how do I find the normal vector for a curved surface, right? So, and to do that, right? So you might still remember that we are going to define a function g of xy, which is equals to z minus f of xy. And then the normal vector is given by the gradient of g divided by the magnitude of the gradient of G. So and you might worry that, okay, do we need to care about the whether the normal vector is pointing up or pointing downward? So there are two choices, but okay, so here you actually don't need to worry about that. But so how do I represent this plane, right? So if I want to represent this plane, so what I'm basically saying is that if I construct any position vector, okay, so which lies on this plane, okay, and it starts at this red point over here. So this is any vector v, right? So lies on this purple plane, and which start at this red point. Okay, so it has to be always perpendicular to my normal vector n. So this is a right angle, always has to be perpendicular. And in general, so how do I represent this v, right? So this v vector can always be written as, so let's say that, right, so the tip of the v vector, so let's say the tip of the v vector, which is here, right? So the coordinate of the tip of this v vector, I will just call this x, y, and z, right? And then at the tail of this v vector, the tail of this v vector over here, right? So what is the coordinate of this point? Of course, it is a, b, and then f of AB. So therefore, right, so the v vector can be written as x minus a, x hat, plus y minus b, y hat, plus z minus f of AB, z hat. So what about the n vector? Okay, so the n vector, as I said, right, so for the n vector, I need to find out the gradient first, right? So the gradient of G is actually equals to, right, gradient of this. How do we do this? Partial f, partial x, x hat minus partial f, partial y, y hat, plus z hat. And remember, this partial derivative are evaluated at x equals a, y equals b. So my requirement, right, so to represent this plane, right, so we can, so that is the equation of this plane is given by this n hat dot v equals 0. Right. Actually, let me purple. Right, so this equation is representing this plane. Right, so because any vector along this plane, right, is perpendicular with the n vector. And that is equivalent to say that the gradient of G dot v is 0. Right. And the gradient of G dot v, you can do it over here, right? So you'll be able to find that. Okay, so I'll just write out the answer. You'll be able to find that this is giving you this. So this is the equation for this plane by making use of this dot product. And again, remember that this partial derivative are evaluated at A and B. Okay. So, and this is exactly the first first order Taylor polynomial for this two variable function. Right? So that everything makes sense, right? So for the one variable function, first order Taylor polynomial is tangent line. For the two variable function, the first order Taylor polynomial is a tangent plane. Okay. So now, making use of this Taylor polynomial, and go back to revisit one of the items that we learned back in chapter 1, okay, which is known as the second derivative test for a function of two variables. Okay. So for one variable function, the second order derivative test, it was easy to understand, right? So you have this second order derivative either being greater than 0, smaller than 0, or to be equal to 0, right? So, and it corresponding to the a minimum point, maximum points, and a saddle point. So, but for this two variable functions, right? So the second order derivative test actually looks more complicated than that, and it seems to be not so transparent why it works this way. Okay, so, and just to remind you, right? So in the second order, I'm sorry, in the two variable functions, so we also have three cases, right? So the maximum point, right? So over here, right? So the minimum point over here, and the so-called saddle point over here, right? So this is neither a maximum nor a minimum, right? So, but the first order derivative, right? So is 0 over here, right? And in chapter 1, right? So I told you that, right? So if these two conditions is satisfied, then it's maximum. If these two conditions is satisfied, then it's minimum. And then if this one is satisfied, it's saddle point, right? So now we are going to try to understand where these formulas comes from. Okay. So, and the key is to make use of the Taylor polynomials that we have just learned. Okay, so, and this time, okay, so we want to include up to the second order the Taylor polynomial. Okay, so we call it this term over here. So, and remember in the last chapter, so we have some x squared term plus y squared term plus some xy cross term, right? So these kind of equations can be written as a matrix form, right? So if that is a row vector, it's the product of a row vector, a matrix, and a column vector. Okay. So try to see carefully, right? So to make sure that you are able to get from here to this form. Okay. So you can do the reverse, right? So if you actually do the matrix vector multiplication, you will indeed able to find this. Okay. So in here, right? So I have this column vector defined as this delta x delta y. Okay, so this delta x is x minus a, and this delta y is y minus b. Right? So this delta x means that, right? So the x distance you are away, right? So from this point A, and this delta y is the y distance that you are away from this B point over here. And now this matrix form, right? So then I this middle matrix, right? So is denoted by H. Okay, so this H actually has a name. Okay, it's called a Hessian matrix. Okay. So notice that this matrix is actually very nice because it's a symmetric matrix. Okay, see that it's a symmetric matrix. And because of the fact that this is a symmetric matrix, remember in the last chapter, we have learned that it can be orthogonally diagonalized, right? So that means, right, so this matrix H, right? So if I sandwich this matrix with this P with this matrix PT and P, right? So it can be expressed as it will become a diagonal matrix T, right? So this is what we learned in the last chapter. Okay, so then well, so you know how to find P and PT actually. If you you just need to find the eigenvalues and the eigenvector of this H, right? So therefore, right, so this form over here, so which is this whole terms over here, can be written like this, right? And then this VTP, right? So and then you can see this PTV, right? So basically is representing a coordinate transformation, right? So here I define this V prime as this PTV, right? So then from here, where I have this non-diagonal matrix, okay, so and then to here, right? So which is a diagonal matrix over here. So that is you can imagine what you're doing is essentially rotating this curved surface, right? So on the XY plane. Okay. So now maximum, minimum, and saddle point, right? So what it really means is that if you have at the maximum point, if you are at the maximum point, right? So that means, okay, if you have if AB is the maximum point, that means if you walk away from AB, so in any direction, right? So you change your X coordinate a little bit away from A, and then you change the Y coordinate a little bit away from B, right? So no matter how you change it, you get a decrease in the value of the function, right? So that is the meaning of being at the maximum point, right? So that means, right? So this whole term has to be always give you a negative number, right? If you are at the maximum point, right? On the other hand, if you are at the minimum point, right? So that means if AB is a minimum point, then again you change your X and Y coordinate a little bit away from A and B, then you always find an increase in your function value. So that means this whole term, right? So will always give you, has to always give you a positive number, right? Whenever you have this X minus A and this Y minus B having some finite, small finite value. Okay. So then finally, right? So saddle point, right? The meaning of saddle point is that it's neither a maximum or minimum, right? So that means if you go from that point to some direction, you might going uphill, right? So just like this, if you are here, if you go in this direction, you are going uphill. You are having an increase in the function value. If you go the other direction, if you are going downhill, you find a decrease in the function value. Of course, you can find many more directions to try, right? So, but sometimes it's positive, sometimes it's negative, maybe. But as long as it's not always positive or it's not always negative, then you can say that this is a saddle point, right? So that's why the thing is, I'm going to look at this term. Okay, so this term again, which is this whole term, and then this term after transformation, which is this term over here. Okay. So this term over here, whether this is the so-called positive definite or a negative definite. So what it means is that if I'm going to actually write it out, so here I can write it this way, right? So the X this delta x prime, delta y prime, because it's after the transformation. And then I have this diagonal matrix now, right? So this D is the diagonal matrix. Right, and this one can be just simply written as 1/2 lambda 1 delta x prime square plus lambda 2 delta x prime delta y prime square. Right. So the question I'm asking is whether this one always give me positive, or this one always give me negative, or this one sometimes give me positive or negative. Right. So that's the question that we are trying to answer. Right. So given some arbitrary delta x prime and arbitrary delta y prime. So you can see that if both lambda 1 and lambda 2 are positive, then no matter what value you pick for delta x prime and delta y prime, the whole thing will be positive. Right. On the other hand, if lambda 1 and both lambda 1 and lambda 2 are negative, then no matter what you pick for delta x prime and this delta y prime, the whole thing will be negative. Right. And finally, right, so if one lambda is positive, the other lambda is negative, then it is possible for you to select the appropriate value of delta x and delta y such that the whole thing will become either positive or negative. Right? So, and that is the case for saddle point, right? So, and the first two cases are the minimum point and the maximum point respectively. So therefore, it really comes down to the properties of the eigenvalues of this matrix. Okay. So, well, of course, you can, if you know all this, you can find out the exact eigenvalues. But here, right, so we just really want to know the sign of the eigenvalues actually, right? So I want to know whether both of them are positive, negative, or both or the two of them have a different sign, right? So then actually let me investigate, right? So the sign of the eigenvalue of this Hessian matrix. So let me write it here, right? So let me just use a slightly simpler notation, partial xx, that means the second derivative with respect to x. Okay, this partial yy, with partial xy, partial xy, right? So this is my Hessian matrix. So eigenvalues. So how do I find the eigenvalue? So I'm going to consider this determinant over here, right? So what is this determinant? Okay, if you go ahead and expand this thing, you will find that it is equals to this. Okay, just expand it, you'll find this. Okay. So now I want to know that the sign of lambda, right? So the signs of the root of this equation over here. So remember, okay, so the last term over here. So you still have, I believe you learned this, right? So if you, in general, if you have a quadratic equation like this, right? So it can be written as this, right? So, and that's why the coefficient in front of this x is the sum of root, right? So, and then this one is the product of root. right? So that's why, right? So over here, this is the sum of root, and this is the product of root. So let me call it this S and call this P. So I want to know the sign of the two eigenvalues, right? So now, if okay, there are three cases. Okay, so and then I'm going to exactly show you how the three cases corresponding to the three cases over here. So case one is that if I have this second order derivative with respect to x to be greater than 0, and also this product P is greater than 0. So if I have these two, so what I can conclude is that this second order derivative for y is also greater than 0. Okay. Can you see why? Right. So because P is greater than 0, so that means this whole thing has to be greater than 0, right? And also this partial xx is greater than 0. So for this whole thing to be greater than 0, so I need this term to be positive, and actually it's a positive number that is greater than this number. But at least I require this one to be positive. Right? So if I require this one to be positive, and I know that partial xx itself is positive, so that means partial yy has also be positive. Right? So in this case, so what do I have? Right, so that means I have both partial xx and partial yy to be positive. And the conclusion is that the sum of root is also positive. Right. So the sum of root is positive, and then the product of root, right? So is also positive as I proposed. So that means the both of the lambda 1 and lambda 2 are positive. Right. So because of this, we have a minimum point. So that's the second. Okay, I should have done the first case first, but this is the second case. Okay, so what I show just now is that the right. So the second case, right? So I have a minimum point. Okay, because I show that the two eigenvalues are both positive. Okay. Using the almost exact the same idea, right? So you can consider the other case, which is the partial derivative, the second order partial derivative of the function is negative. But the product of the root is still positive, then you are able to show that both of the lambda is smaller than 0, and that's why you have a maximum point. Okay. So finally, right? So for saddle point, is that if I have this product P to be smaller than 0, so what does it mean? So the product of the two roots is smaller than 0. So that means one has to be positive, the other has to be negative, right? And therefore, that gives the saddle point. Okay. Right. So from our knowledge in the diagonalization from last chapter, and also the Taylor polynomial that we just learned. Okay. So now we at least have some understanding. Okay, on how this second order derivative works. Okay, so that you have learned in the first chapter. Okay. So this is the end of this part 2 of this chapter. Okay, so we only have one more part to go, but I will just do it on Wednesday. But actually here I would like to talk a little bit about complex number. Okay, so and it is related to the Taylor series that we have just learned. Okay, so I in the second order differential equation in this in chapter 4. So I at some point I think I throw out a formula like this, right? So without any explanation, right? So and here I want to say a bit more about this. Okay, so based on the Taylor series that we have learned. Okay, so remember the Taylor series that we have learned is that e to the x is 1 plus x squared divided by 2 plus x cubed divided by 3 factorial and so on, right? So in fact, right, so we just basically take this infinite series as the definition of this exponential function, and then we allow the input of this function to be this complex number over here. Okay, so then what we will have? Okay. So that is, we put x equals I theta. So then what you realize is that e to the I theta would be 1 plus I theta plus I theta squared divided by 2 factorial plus I theta cubed divided by 3 factorial and so on, right? And over here, you can see that we do have I for every term, except for the first one, but it's I to the some power, right? And here, well, you notice that, right? So if I have this I to the 1, I to the power 1, it of course just I itself, and then if I have this I square, actually I have minus 1, right? If I have I cubed, then I will have minus I, and if I have I fourth, I get back to 1, and then that's why if I have I to the power 5, then I will have I again, and so on. So from this, okay, so you can see that each term, right? So I will either have an I or minus I or 1 or minus 1. So and eventually, right? So you see that I can actually group the terms like the first term, which the first group, or sorry, the first group that does not contain any I, right? So because whenever I have this even power, then I don't have an I, right? So and then the second group, which always come with an I. Okay. So you can try to actually do the first few terms. You realize that you can, well, you can group the terms like this. Okay. So find it like this. Okay. So and then you will also realize that this first group is actually the Taylor series of cosine x. And then the second group is the Taylor series for sine of x. Okay. So that is the e to the I. I'm sorry, not cosine, not x, but yeah, my mistake, not x theta. Right, theta. So that's why e to the I theta is cosine theta plus I sine theta. Okay. But of course, this is not the rigorous proof, right? So for this thing, but at least try to understand where it comes from, right? So this is known as the Euler's formula, right? So and well, I'm sure that you see it again, right? So especially when you learn about waves and in quantum mechanics and so on. So so then at least I want to just quickly tell you how to do some basic math with this, right? So and whenever so some basic properties is that so you know that this if you have this e to the x1 times e to the x2, then basically what you have is e to the x1 plus x2, right? So actually this rule also works for complex numbers. So that's why if you have e to the I theta times I theta 1 times e to the I theta 2, you will actually be able to just simplify e to the I theta 1 plus theta 2. Okay. And also, right, so whenever you have a complex number, right, so you can always draw this complex plane, right? So this is my complex plane over here, and this is my complex number. Suppose this is x plus iy, right? So and such a complex number, right? So can always be written in the following: is that so this is I define this angle to be theta, okay, and then this the length of this line, okay, which is the modulus of the complex number. I call this r, okay. You know that this r is just the square root of x squared plus y squared, right? So, but anyway, so this complex number, right? So x plus iy, but can always be written as r cosine theta plus I sine theta, right? So that's just like what you do with vector actually. And I just told you that this cosine theta plus I sine theta, right? So using Euler formula is e to the I theta. Right? So this is the exponential form of a complex number, right? So any complex number you write down x plus iy can be always converted to this r times e to the I theta. Okay. So and also you can do differentiation. Okay, so if I have this e to the I theta, okay, so this is just treat it as a function of theta. Okay, so you can actually take derivative. Okay, and just like what you do with an exponential function. Okay, so you will basically have this I times e I theta. Okay. And you can compare, right? So because e to the I theta is actually, right, so cosine theta plus I sine theta. Right, so this one, if you just do it by using sum rule, by do it term by term, what do you find? You will find that it's minus sine theta plus I cosine theta. Right. If I just take the common factor out, I, then what you have is cosine theta plus I sine theta. And this one, again, equals I times e to the I theta. Okay. So that as expected, of course, you do it this way, you obtain this answer. Do it the other way, you should obtain the same answer, right? So and sometimes, right? So this property, right? Cosine theta. I'm sorry. E to the I theta equals cosine theta plus I sine theta give us convenience. Okay, is that if you just take the derivative for the cosine or sine, right? So you every time you take it, you need to change from cosine to sine, and then from sine back to cosine, right? So, but if you just take it with the exponential, all you need to do is to pull a factor of I down here, and then at the end of the day, right? So you can just take the real or imaginary part that you need. Okay, so I'll stop here for today. Okay, so then I'll see you on Wednesday. Okay, for the last part of the chapter.